When a critical application freezes, drains a device's battery, and triggers cascading server overloads, the hardware is usually just reacting to a set of instructions it cannot escape. The assumption is often that malware or an external hack is responsible. In reality, these failures are frequently caused by a hidden structural anomaly buried deep within the software's own data architecture. This animated diagram shows a fundamental computing structure known as a linked list. It is a simple chain of data. Instead of keeping all information in one giant block, each piece of data, or node, contains a specific value, along with a directional arrow pointing directly to the next piece in line. The structure relies on linear progression, but if a single pointer is misdirected, if the tail of the list reconnects to an earlier node in the chain, that definitive endpoint vanishes. The straight line becomes a closed circle. A standard computer algorithm is designed to read this list until it hits the end. Because the end no longer exists, the algorithm gets trapped forever. It reads the same nodes over and over, hoarding processing power until the system's resources are exhausted. Linear data structures containing these hidden cycles cause applications to hang indefinitely. Solving this requires a detection mechanism that can signal the loop's presence before system resources are drained. The logical problem is straightforward. How do we track where we've been in a massive dataset to identify the moment we start moving in a circle? As the program reads the list, it drops a copy of every visited node into an external hash set. The exact moment the indicator hits a node already recorded in the container, the system flags a match. The cycle is caught. This chart plots dataset size against memory usage to illustrate space complexity. By copying every node, the memory requirement grows at the exact same rate as the data size. This is known as O of n space complexity. For small lists, that extra memory is trivial. But for enterprise-scale networks processing millions of nodes, duplicating every piece of data can cause the server to run out of memory. The tracking system itself creates the very resource exhaustion it was meant to prevent. For a fix to work at this scale, it must identify the cycle without using any auxiliary memory, maintaining an O of 1 space complexity. To bypass the need for storage, we can stop looking at the data as a static record and instead look at the relationship between two moving points. In the late 1960s, computer scientist Robert W. Floyd popularized a solution known as the tortoise and hare algorithm. It deploys two independent tracking pointers simultaneously on the exact same dataset. This diagram shows the traversal rules. The slow pointer moves one step at a time.
The fast pointer moves 2 steps. If the path is straight, the outcome is simple. The fast pointer reaches the end, hitting a safe termination signal. Because the fast pointer acts as a scout, the algorithm confirms the entire data path is safe and terminates. It does this without requiring a single byte of extra memory storage. In a cyclic list, the physics change. Once both pointers enter the loop, they are trapped. Moving one node faster per turn, the fast pointer closes the gap from behind. Eventually, they occupy the same nodes simultaneously. When they collide, the cycle is confirmed. This diagram shows how that logic translates directly into code. The algorithm uses a simple loop to check if the fast pointer has reached an end. Inside that loop, a single condition checks for the interception. If slow equals fast, return true. By simply comparing the position of two variables, the program identifies the infinite loop. It avoids copying millions of data points, neutralizing the threat without taxing the system's memory. The fast and slow pointer technique resolves the memory scaling issue by using the simple logic of relative velocity. It proves that a data problem can often be solved more efficiently by treating it like a race on a track.